students, so 5.6, a topic called reverse substitutions, and you'll notice an asterisk in your pack which says that these types of questions will not be on your exam, but we're still doing them, and I want you still to go through this because it will give you an even better understanding of integration. It's really good practice, and yeah, if you can do these, then you can do any of the questions on the exam. So, why is it called reverse substitution? Well, instead of using a substitution u equals f of x, we use a substitution of the form x equals f of u. And the first thing I'd like you to do is just have a go at this. So for this question on the screen right now, you can see the substitution is x equals tan u, and I'd like you to try and work through this integral and see if you can come to an answer. Once you've done that, we restart the video and we'll go through it together. Okay, so you've had a go at this first question, and we're going to do that together. Before we do, I just want to emphasize this point about the fact that if the substitution is happening in reverse, so x equals f of u, we need to ensure that the function is one-to-one in the domain we're looking at. And that's because the real substitution we're doing, if you like, is u equals f inverse of x. And what we need is the inverse function to be well defined. So we need f dash of x to be a well-defined function. Sorry, f inverse of x to be a well-defined function. And obviously we know that even though a many-to-one mapping is a function, its inverse is not well-defined and it's not a function. So to make this kind of substitution, we need to be a little bit stricter. And we'll touch on that as we go through the questions. So for this first one, they gave you, or I gave you, the substitution to try. But if we look at why we might do that, well, we might choose x equals tan u because we know that we have a identity for tan squared plus 1. And really that's the clue that tells us to try x equals tan u, because we think that our identity might make this easier and get towards an integral we can do ourselves. So what I'm going to do is I'm going to try x equals tan u, which means that x squared plus 1, well, that's tan squared u plus 1, which we know is sec squared u. And then the other thing that we know here is dx by du is sec squared u, which tells us that dx equals sec squared u du. And if I'm looking at this, I can take my dx and swap it out, and I can take my x squared plus 1 and swap it out, and so I can change my integral I. So it's now the integral of 1 over sec squared u times sec squared u du. So it's, look how easy this is, 1 du. So it's just u, so it's just tan inverse of x plus c. And that's our final answer. So hopefully you can see how that's a pretty neat thing. Just notice the restricted domain. This tells us that we have a one-to-one function, and so is important. Okay. Using that idea, I'd like you to try the one underneath. The one underneath is going to use exactly the same substitution, but actually it's not quite so simple when we get our integral, and you need to do a little bit of extra work to get the final answer. So there's a good step in the middle, something that we have done before, but it might not occur to you straight away. But see if you can get all the way through to a solution that is, in terms of an inverse tan like this, but then also just has a regular function for x. And just because it's like an easy way out, that's not going to be a nested inverse function. So you can write your solution as something like sine of tan inverse, but don't do that. See if you can find a way just to write it in terms of x. Have a go, then unpause the video and we'll go through it. Okay, so you're going to use exactly the same substitution as before, and I'm not going to write out all the extra bits then, right? Because we've already got those from the previous question. But what that means is we're going to have 1 over sec squared of u squared times sec squared of u du, which means we're going to end up with like 1 over sec squared, because one of these cancels, and 1 over sec squared is just cos squared u du. Now what I'm hoping is that at least some of you, when you saw the cos squared, you think, oh yeah, we know how to deal with that. We're going to use the identity cos 2u equals 2 cos squared u minus 1, which means that cos squared of u is a half times 1 plus cos of 2u, like this. So that's going to give us a half times the integral of 1 plus cos of 2u du, which, when we integrate that, is going to give me a half u plus a half sine of 2u, but because of this 2, that would actually add an extra half to make this work. So I'm actually going to end up with a quarter when I simplify it, and plus c. So a half u plus a quarter. Now what I'm going to do is, because I don't really know how to deal with sine of 2u, I'm going to use that identity of sine 2u equals 2 sine u cos u. So the 2 is going to cancel with a quarter, I'm going to get a half, but the sine u and the cos u I'm going to evaluate now. So this is the trick that I was talking about just beforehand. We know that tan u equals x. So in other words, the opposite over the adjacent is x, so we can call these x and 1. Our hypotenuse is square root of x squared plus 1, which tells us that sine u equals x over root x squared plus 1, and cos u equals 1 over root x squared plus 1, like we've done before. So simplifying my answer here, u, just like in the first example we did, is tan inverse of x. So that's a half tan inverse of x for the first term. And then we're going to have a half from the quarter and the 2 times by sine u cos u. So that's x over x squared plus 1 plus c. And I guess that's our final answer there, or we could just simplify it a touch by saying a half times tan inverse of x plus x over x squared plus 1 plus c. And that'll be my final solution. Now, that's not an easy question, too hard for the exams, but like I said, if you can do that, you can do anything. I'm going to look at one more, and then we're done for today. Okay, so in this question, you're going to use a different substitution. It's not going to be x equals tan u anymore, but what I'd like you to do is have a go and see if you can find that substitution for yourself that simplifies the integral, and then work it through. Have a go, then unpause the video when you're ready to go through it. Alright, let's do this. So we're looking at what kind of substitution do we need. Well, this expression reminds us of trig, and we're thinking now about the Pythagorean identity cos squared plus sine squared equals 1. And in fact, if I make the x something like 2 sine u, I'm going to get 4 minus 4 sine squared. So in other words, that's going to be 4 cos squared. And that's going to be my way into this. So I'm going to let x equal 2 sine u. So therefore, 4 minus x squared is going to be 4 times 1 minus sine squared u. So that's 4 cos squared u. Dx by du is 2 cos u. So dx equals 2 cos u du. And hopefully you figured out that because this is a definite integral, the third thing we need to look at together is what those limits change to. So this is defined in terms of x, so x is 0 or 2, and we need to look at the function here. So if x is 0, sine must be 0, so u must be 0 as well. If x is 2, that means sine u is 1, which means u must be pi over 2. And so we look at this, we've got our new limits. Whenever we do a definite integral, and by substitution we need to change the limits, we have our dx, which is going to change out, and then we have our 4 minus x squared, which I can put underneath. So we have those 3 parts to switch out. So our integral is now going to be the integral between 0 and pi over 2 of the square root of 4 cos squared u, so that's just 2 cos u, times by 2 cos u du. So in other words, that's 4 times the integral from 0 to pi over 2 of cos squared u du. And then just like in the previous example, I'm going to use my cos squared identity. So my cos squared identity was a half of 1 plus cos 2u. Got that the right way around, I'm just checking it, yep. So a half is going to cancel with the 4 to give me a 2. Still going between the limit 0 and pi over 2. And now I'm integrating 1 plus cos 2u du. So this is 2 times square bracket for the integral u plus a half sine 2u between pi over 2 and 0. Now when I think about substituting these limits in, for both 0 and pi over 2, the sine bit is going to be 0, so that's going to disappear. The u is also 0 for substituting in 0. So actually, of the 4 terms, only the first is going to be non-zero and survive. Whoops, sorry, I missed it off the screen. So my answer, you can just think about the substituting in yourself if it's not obvious straight away. It's 2 times pi over 2, so it's just pi. And that's our final answer. So, yeah, a great topic, really, hopefully, interesting questions for you that start to show you just how powerful you've become in terms of calculus in quite a short time, and how actually you can now use quite complicated techniques in order to solve tricky questions. As always, if you get stuck on anything in this session, just put it in the exit ticket and we'll try and go through it the next time we have a chance together. Best of luck with the exercise, and speak to you all soon.